You guys did very well. Finishing it strongly. I know it was a lot, especially the JIPipe, but you learned a lot, we hope, and then you continue using knowledge that you gained here. As we later, if you have questions about either part, you can always email us, contact us with questions that we'll be very happy to answer. I will quickly go through the answers to the microscopy part, and then Ruben will show his solutions. It was not difficult, but it required some attention. The first task, all but two got it perfectly right. Namely that you just had to apply the rules that we learned about on Monday morning, how a double convex lens forms an image. And the general light paths, of course, were, for example, going through the center, will not change the direction of the light, and going parallel, will go through the focal point on the other side of the lens. This you all got correctly. And then when we put a second lens, it will use the first image as its object and generates a second image. Like I said, n-2 got this perfectly right, so you get an inverted, magnified, and virtual image. Virtual because it's on the wrong side of the lens, so you cannot collect the light. You need an observer or a camera lens here to form an actual image. This went very well. It was also interesting to observe the solutions that some of you did not repeat the first focal point to the same extent on the right side, which meant it was imagined to be an asymmetrical lens, which does exist, it's not a problem. But with that, you could also generate an image which was actually in the right side of the second lens, so it was a real image. You still get a full score for that. Although typically, with a symmetrical, not typically, with a symmetrical lens, the two focal points left and right are missing. But I did not consider that as a problem. Okay. And of course, we learned that these lenses are complex inside. It's not a single lens. We talked about that, and then we briefly went through during the lecture of what these labels mean. And these were the two lenses you guys had to work with. You did well, of course. This was not terribly difficult. I just wanted you to repeat, to go through what is what means what. And you all got these parts right. One of you asked if this is the serial number. Yes, it is the serial number. So you can look this up in the catalog and it will tell you what exactly the lens is like, or how to characterize, for example, the transmission curve, point spread function, and so on and so forth. One interesting point was this correction color. This one does not have one. It's an oid immersion lens. This one has one, and some of you did not go into details. Some just listed what possible roles this color has. In this particular case, it sets the thickness of the cover slip that sits on top of the sample. If you remember, a typical one is 170 micrometers. That's a so-called 1.5 thickness cover slip. When you work in microbiology, you will meet with this numbering system. The correction goes all the way down to 0.11 millimeters on 10 micrometers. This is the number 0 cover slip. It's very, very thin and very easy to take. But for some super resolution techniques, this is actually required to be applied. So to have it thinner and extremely precisely manufactured. And if you go on the higher side, it goes up to 130 micrometers. If you have such a color and you don't set it right, and some of you answered properly on that, this will ruin the point spread function, basically, not ruin, but makes it worse than it could be and should be. So it's important that you set this up properly. The other point was many of you, or some of you at least, went into some details on that, which I appreciated, that depending on the lens type, this color can have other roles. For example, in the one I showed at the lecture, which is a multiple immersion lens, it can be used with glycerol, water, and in the back there is a symbol for oil. So you can use with any of the three immersion liquids. The role of the color is to set up what immersion liquid we are using. And this is a very, very practical lens. It's very expensive. It's about 20,000 euros or so, where it's new. And for a lab or microscopic work facility, this is very, very useful because I can match the refractive index of my sample really well. So my sample could be, for example, live imaging or cells in a petri dish, in which case they are basically in water or saline. It could also be a sample which is, for example, in vector shield, which is basically a 1.4, 1.41, 1.44 refractive index that corresponds to glycerol. And in this case, you would actually put glycerol as an immersion. And finally, if you use a sample where you need very high resolution, but the sample itself is not either in water or vector shield, but rather very, very close to the cover slip, so the light does not travel through the mounting medium of the sample, then you would use oil, and in this case you would turn this one to oil. If you don't set this up properly, you have the same effect as here, namely ruining the quality of the image. These were the answers for this one, and you got this one right. The next question was about one of the most important parts of the microscope, namely the dichroic tube, how this is built. We talked about this, that thanks to the Stokes shift, we are able to separate excitation and emission lights in fluorescence microscopy, but that also means that we need these optical elements as part of the microscope, and they are positioned behind the objective lenses, so either above them on an inverted microscope or somewhere down here on an upright microscope. And because, as with the next question you also realized, we do need more than one color in a typical experiment. We also need more than one of these. So in a typical microscope, you have several of these in a rotating turret, on which you can, just by pushing a button on the software or on the microscope itself, you can rotate this turret and put the proper dichroic tube in the light path. So it matches the fluorescence excitation and emission that you want to work with. Many of you mounted on the mounting thread here. Yeah, it is correct. These filters can be changed, so you can unmount these either the excitation or the emission filter and build your own cube without having to buy the metal part again and again and again. Otherwise, these guys basically just pop in. So if you work in microscopy, you will see this. They pop in quite easily, so you can change the configuration of your microscope if you have an unusual color in your sample. So this is not an obstacle. Keep in mind that if the microscope per se doesn't have the color that you exactly need, then you can buy such a cube for about €1,000 and then replace the existing one. And the inside the cube, we already know, and you all answer this properly. You have the excitation and emission filters and the dichroic. And with some of you, we discussed yesterday that the dichroic mirror itself doesn't necessarily have to be always like this, which is a long pass where below this critical wavelength it reflects, and above the critical wavelength it transmits through. But rather, this part can be made of bands themselves, and then you have yourself a dichroic cube that works with more than one color. With fluorescence microscopy, for example, we do not have time to have a separate cube for every color. Let's say you have red, green, and blue labeling on your sample. You can choose a dichroic cube that has the ability to pass the light through with the dichroic three different bands. And then you can say, okay, I want the cube which is designed for 488, 514, 561, for example, or 633. And the next question was about confocal microscopy and the role of the pinhole. You, of course, all remembered what the pinhole does by cutting out the outer focus light. And you also remembered that opening the pinhole basically turns the confocal microscope back into a wide field microscope. What I was really looking for as an answer, and I got it from one or two colleagues, was that the optimal size of the pinhole from the point of view of resolution, which is the question, is 0. The practical optimal is 1 area, but the theoretical one, from the point of view of resolution, is 0. I only took like half a point off, or not even that. If you didn't get this right, because practically, indeed, we operate this at 1. But if you look at the curve, and if you remember the curve, at area unit 1, we are not at optimal resolution yet. We have another 25 to 30% to gain by closing the pinhole completely. This you all pointed out well, that if I close the pinhole, I get better Z resolution, but I lose light. And you were perfectly fine, so you got full score for that. And that led to the logic of why we use smaller pinholes. So there was a comparison, you remember from the lecture, but more importantly, why did we have size area scan technology? And this was very well described with basically all of you, with the arrangement of 32 micro PMTs, basically. One of you even described what these are made of. And practically that will increase practically will increase the resolution by a factor of square root 2 after processing. And as you also got right, the processing is basically a deconvolution process. So you take advantage of having a signal from various area unit size pinholes. Instead of using the pinhole itself, you get more photons, and with the calculation you also get a higher resolution. So this was done very well. But this, like I said, linked back to this curve that I cannot measure at 0 pinholes, so I need to measure this curve along various pinhole values. And what I don't want to use is, what I don't want to do is take the same image with pinhole. What I have, 1, 0.7, 0.1, it takes forever. So instead, you do that, and then from here on, it's just a question of a few seconds or minutes to analyze the photon signal from each of these mini PMTs and then calculate the theoretically optimal image. Okay, and then this is what you remember this from the lecture. The next question was about fluorescence and the Stokes shift and how the diagram looked for a single photon excitation, and you got this one right. Here, the only point was that you remember that after absorption, there is a certain level of energy loss. So the photon that goes in has a slightly shorter wavelength than the photon that comes out. So there's a shift towards the red end of the spectrum. Some of you also talked about phosphorescence, which we completely didn't mention, but you got all full score for this one. And then we had to design an experiment. And this was the most challenging one. You all did well on it, but this was the one that made you think. And that was the purpose of the question, not because you could not get the information very easily from the internet. And the idea was that when we use more than one color, more than one label, then eventually we get to the point where the absorption and emission spectra of the labels, and in this case we had live cell fluorescent proteins, cyan, yellow, and red, over. This is unavoidable. And then what I was looking for in terms of answer was that if I have three fluorescence labels, I need to know their spectra, not only the peak values of the spectra, to be able to design the experiment. And we discussed this live during the lecture, the homework period yesterday, that if I just tell you, okay, the excitation peaks are at 420, 488, and 510, for example, or 530, 550, based on that, you can estimate your excitation needs, what lasers you will need, for example, but you will not be able to design your filters. You will need to know what the spectrum looks like for each of these labels, how wide they are. And the reason is that eventually they start to overlap. I just have an example for 2, but you very nicely got the figures for 3, but this is easier to explain. So basically, with CFP and YFP, for example, to excite them separately is not particularly difficult, because the excitation spectrum of CFP, although it does overlap with that of CFP, I can put a filter here for the excitation that avoids this overlapping area. Now, if I use a laser, then I simply design my input to be around 410, 420 nanometers, so it's a violet laser. If your light source is an LED, then it's even easier to find a relatively cheap light source for this range. And I will choose one around 520 or so, or 510 for the CIP. And then your red fluorescent protein comes in somewhere here for the excitation. So at the excitation side, we are probably okay. The problem then comes on the emission spectra, which unavoidably overlap quite a bit. And then you have a problem. You can, of course, set up your emission filters. And this actually is important even in laser scanning confocal microscopy, because the lasers are monochromatic, but the emission is, of course, not. For example, like this. And this way, you would say, okay, I'm probably avoiding the crosstalk between CFP and YFP, but you are probably not, because your YFP emission filter still picks up some of the CFP, quite a bit of it actually picks it up. And if you have the RFP on the continuation, that will pick up quite a bit of the yellow fluorescent protein signal. So this is unavoidable. And practically, you also saw this with Roman's homework, which was from a data set which I worked with a colleague, where you had macrophages and neutrophils, and you had to then subtract the 2 ROIs from channel 2 and channel 3 to avoid the crosstalk from the neutrophils. It's been red to the orange one. Remember this from yesterday. That was exactly the case what we are talking about here. So with live cell microscopy, where you don't necessarily have the chance to have just a control label that you very nicely described, where you only have one label, or you only have 2 labels out of the 3, and you can measure the crosstalk. You still need to be able to do microscopy. And then you have to live with the fact that there is a crosstalk. And in this case, it comes to you as an image analyst, which you now slowly become, to get rid of this crosstalk, like we did yesterday with the exercise. So we have 2 options then to avoid this mess. And one is, as I said, do control samples, and you all discussed very, very well. And with fixed samples, this is actually the way to go. If you have your certain secondary antibodies, for example, of which you know the spectra very well, you will make samples which are not labeled at all, labeled with one fluorescence label, or with two, but you measure the signal from every channel that you are going to detect, and this way you know how much, for example, of the blue goes into the green and red, or how much of the green goes into the red, and so on and so forth. With live one, where you express fluorescent proteins, you're probably not going to develop a mouse model that develops only CFP but not the YFP, because the whole model development will take you months. So in this case, one tool is, and this was mentioned by one or two of you, was to make these spectra, the emission spectra, narrow, not the spectra, the emission filters narrower. If I make it narrower, I avoid and shift it as far as possible away from the other fluorescent proteins, I get less crosstalk. But I also get less light. So this is a compromise, but it's a realistic chance. And on laser scanning confocal microscopes, for example, I have the complete freedom to set, on some microscopes, I have the complete freedom to set up the emission wavelength range from which I detect. I use so-called spectral detectors, and the spectral detector is basically a photomultiplier in front of which there is an optical device which will spread the light into its color components, like a rainbow, which you split the light of the sun into a spectrum from violet to red, and then it puts either a physical slit, a cut in a piece of metal, in front of this resolved light, and then selects a certain range of wavelength for detection, or this is its ice wave, or it uses an optical crystal, an optical crystal, where the transmission curve of the crystal can be controlled electronically by setting the frequency of an ultrasound. But either way, the point is I can have full control of the width of these emission range from which I detect. And this way I can actually narrow this down so much that I avoid most of the cost. But like I said, you lose light, but you now also know that with image analysis you can improve your images quite a bit afterwards. So you don't have to be perfect with your experiments. You have to reach your biological goals, get the signal, get the time resolution, get the spatial resolution, but your signal to noise ratio can be improved afterwards with various either classical or deep learning based methods. And this you got right. Like I said, from a couple of you also got the answer about the width of the spectrum, which I appreciate. And this is just a reminder of the main message from this half a day of lecture, that these 4 points of view or concerns you keep in mind all the time, but you are not going to be able to satisfy all 4. Something has to give. And the reason why you really have to, I always recommend this to colleagues, even in biology, learn about image analysis, is that you know what you can do afterwards. Because that will tell you how good you have to be with your microscopy images. And again, you cannot be perfect and you don't have to be perfect. You can do a lot afterwards. This was my message. You did all very well. Congratulations. I was really enjoying time with you guys. And now Ruben will tell you about the even more exciting JIPipe tasks.